Have you ever actually stopped to think about how your seafood gets to you? And no, I don't mean the truck ride from the grocery store to your fridge. I'm talking about how the industry physically moves hundreds of thousands of living, breathing fish from a freshwater hatchery all the way out into the open ocean. If you think it's just about, filling a tank with water and hitting the road, well, think again. Moving live fish is an incredibly high-stakes biological logistics problem. Honestly, it's way closer to engineering a life support system for astronauts than it is to driving a standard delivery truck.
Take these massive wellboats, for instance. These aren't just your average cargo ships. They're highly engineered, floating spaceships built specifically for aquaculture. When you're dealing with this sheer volume of live cargo, every single drop of water, every fraction of a degree in temperature, and every tiny bubble of oxygen has to be perfectly calibrated. One minor miscalculation, you could literally lose everything on board.
So welcome to This Explainer. Today, we're taking a deep dive into the fascinating, microscopic, and highly pressurized world of live fish transportation. We're going to follow these fish on their hero's journey from the freshwater farm out to the sea cages and break down the absolute cutting-edge science keeping them alive along the way.
Okay, let's dive into this. We've got a lot of ground to cover today. We're going to hit on the smolt transportation boom, how we actually prep the fish for the journey, the delicate chemistry of survival, the high-tech fish taxis they ride in, and finally, we'll wrap up with the invisible contagion threat.
All right, part 1, the smolt transportation boom.
So why is this specific industry booming right now? Well, it's because aquaculture has undergone this radical shift toward extreme specialization. It used to be that a farmer handled pretty much the entire life cycle of a fish in one single location, but not anymore. Now you have separate facilities just for hatching and entirely different ones way out in the ocean for growth. That means these young salmon, which are called smolt, have to travel massive distances. To put that into perspective, just look at these numbers from Norway. Over just a single decade, the number of smolt farm licenses actually dropped from 254 down to 220. But the production volume? It nearly doubled, rocketing from 89 million up to 165 million smolt. So we're seeing fewer facilities, but dramatically higher density. And this boom has created a massive logistical bottleneck. We suddenly have to move way more fish over much longer distances safely.
Moving on to part 2, prepping for the journey.
So how do you actually prep a live animal for this kind of intense trip? You might assume you'd want them well fed and energized, right? Actually, it's the exact opposite. The biology here requires some pretty counterintuitive prep. Farmers literally have to starve the fish for a minimum of 2 days before transport. Here's why. If you fast them for the perfect amount of time, they empty their digestive tracts. If you don't do this, or if the journey goes long and they start breaking down their own protein to fuel their metabolism, they produce ammonia. In a closed tank, that ammonia will very quickly build up to lethal levels. So starving them is actually a strict, life-saving measure. It stops the fish from accidentally poisoning their own closed air supply.
And honestly, ammonia isn't even the only threat. These smolt are incredibly delicate. The physical netting and pumping processes have to be handled with extreme care using soft, knotless nets. Why? Because if a fish sheds even a single scale by brushing against a rough edge, it opens a gap in their biological armor. See, the fish naturally has a lower salt concentration than the seawater it's moving into. So that one missing scale can trigger what's called osmotic stress. It's this fatal condition where the fish essentially leaks its own water out into the surrounding salty ocean. Like I said, they're exactly like astronauts in pressurized suits. One tiny tear and the results are catastrophic.
Okay, section 3, the chemistry of survival. Once the fish are successfully loaded into the tank, we shift away from biology and get into the invisible physics of their environment. Temperature, oxygen, and pH must be perfectly balanced. For instance, favorable transport pH is slightly acidic, usually between 6.5 and 7.0. But fresh seawater, that sits higher, around 8.2. So you might think, hey, if the water in the tank gets a little dirty during the drive, let's just pump in some fresh seawater to flush it out. But no way. Doing that can literally wipe out the entire tank. Here's the chemistry behind it. Fish excrete ammonia. And at a lower pH, that ammonia reacts with water to form ammonium, which is much less toxic. But if you suddenly introduce higher pH seawater, it alters that chemical balance, instantly turning that ammonium right back into highly toxic ammonia. It causes acute, rapid poisoning. You can't just casually change the water, you have to actively manage the chemistry. Because of this, transport is basically an ongoing, high-stakes math problem. Let's look at an example straight from the source data to see just how incredibly tight these margins of survival are. Imagine you need to transport 100,000 smolt. Let's say each one weighs 100 grams. You're using a 10 cubic meter tank truck, and you absolutely need to keep the water chilled at exactly 10 degrees Celsius so the fish consume less oxygen and excrete less toxic gas. If you calculate the density and the time on the road, how much pure oxygen do you think you have to pump into this closed system for just one single trip?
Turns out you need a staggering 2.5 kilograms of pure oxygen just for one trip, and that is strictly to keep this dense biomass breathing. Because here's the real kicker. The oxygen diffusers in these tanks, they only have about a 20% efficiency rate. That means 80% of the pure oxygen you pump in just bubbles straight up through the water and escapes into the air without ever being breathed by a single fish. You literally have to carry and pump 5 times the required biological oxygen just to guarantee they survive the ride.
Which brings us to Section 4, high-tech fish taxis. For shorter trips on the road, we're talking usually under 10 hours and kept very cold, under 8 degrees Celsius, the industry uses heavily insulated tank trucks, and they use a brilliant closed-loop system. This isn't just a tub of water sloshing around. You have active water circulation pumps pulling water through particulate filters to catch solid waste, chemical filters to manage that pH we talked about, and an oxygen cone forcefully mixing pure oxygen from a high-pressure tank directly into the water supply. It is quite literally a mobile intensive care unit.
But what if a truck just isn't going to cut it? What if you're crossing oceans? Well, then you contrast the truck with the massive wellboat. These are the undisputed kings of fish transport, boasting some incredibly advanced features. We're talking onboard refrigerated seawater systems, protein skimmers, chemical pH regulation, and even ozone and photoozone water treatment to completely neutralize potential contaminants. They even feature movable bulkheads inside the tanks. This means they can gently push the fish out using water pressure or siphons when they arrive, which entirely eliminates the need for stressful fish vacuums or physical nets.
Finally, Section 5, the invisible contagion threat.
Now, as amazing as all this technology is, these vast logistics networks can accidentally become contagion highways. If we break down how disease spreads in aquaculture, you have vertical transmission, so parent to offspring. You have horizontal direct, meaning one sick fish bumps into a healthy fish. But the massive blind spot for the industry right now is horizontal indirect transmission. This happens when disease spreads via shared equipment, shared water, or shared wellboats. The very vehicles designed to keep these fish alive can inadvertently become the thing that kills them.
There's this fascinating and honestly kind of chilling detail from the source material. Researchers were investigating disease outbreaks and kept finding these blind passengers, species like wrasse and rainbow trout, living in salmon cages where they had absolutely no business being. So how did they get there? Well, the logbooks revealed the truth. These imposter fish had been transported by the exact same wellboat prior to the salmon delivery. They managed to hide inside the complex plumbing of the wellboat, and get this, they actually survived the harsh, mandatory chemical wash and disinfection process between farms. They were then just accidentally flushed out into a completely pristine, uninfected farm.
Which leaves us with this pretty provocative, unsettling thought. If a fully grown, live imposter fish can survive a chemical disinfection wash simply by hiding deep inside the plumbing of a high-tech wellboat, what microscopic, invisible pathogens are currently surviving that exact same wash? The more complex our life support systems get, the more places there are for bacteria and viruses to hide out. It really makes you stop and wonder about the fragility of our global biological logistics. The next time you look at a piece of salmon, I guarantee you'll have a newfound respect for the incredible and perilous journey it took to get there. Thanks so much for joining me on this explainer, and keep questioning the incredible systems running our world.